Right. Thank you guys for coming to the long-form variant of this talk for financial crypto, mining for privacy, or how to bootstrap a snarky blockchain. And so this talk is primarily about so-called structured reference strings for ZK snarks and how to securely generate them. Specifically, we're focused on a type of reference string called the updateable reference string, which have some fairly nice properties that allow us to do this in a much easier way. And we will discuss in this talk what updatable reference strings are, why they're interesting, how we can securely construct them from a blockchain protocol, and what practical issues arise in that process. And there's two practical issues we'll focus on. The first is how you need to parameterize things for this to make sense. And the second is how to address the misalignment of incentives, which will naturally arise unless something is done to stop it. And so let us start off with the problem. And it's a problem which has been fairly well understood in cryptography for a while now, which is if you want to have a non-interactive zero-knowledge protocol, you need some form of common reference string. Now, for many non-interactive zero-knowledge protocols, a random reference string is sufficient. So a string consisting simply of random bits of some length is enough to do non-interactive zero-knowledge. But unfortunately, for a lot of ZK snarks, so for a lot of the most efficient zero-knowledge protocols that we have, more is necessary. And in particular, more means they need to have some structure to them. And how this looks like in practice is that not only is the reference string structured, but this structure has a trapdoor. So there's some information about the reference string, which in creating it, you also create this additional trapdoor information. And the issue that mainly arises is that this trapdoor information can be used to break the security properties of the snark. Specifically, usually the soundness property can be broken, which means you can prove whatever you want to prove, and that's obviously an issue. So the sampling of these reference strings presents a single point of failure for non-interactive zero-knowledge systems, or specifically for snark systems, because it both has to be done to get non-interactive zero-knowledge in the first place, and if it is done insecurely, your non-interactive zero-knowledge protocol is not sound. So there's been a lot of prior work on how to actually do this, and this is a paper by the guys at Zcash who have really pioneered this field, because they have had to practically do the sample the reference string for a ZK snark twice. And essentially their core idea is to run a secure multi-party computation protocol with multiple participants from disparate parts of the globe, and to say, well, at least if one of these participants is honest and behaves honestly during the protocol, we know that the trapdoor will be erased and will have been deleted, because no one party can reconstruct the entire trapdoor, or no, sorry, not even no one party, no subset of parties can reconstruct the entire trapdoor amongst themselves. It needs to be collusion among all parties to do so. And this is what Zcash did in its first phase. It had a group of 6 people who were selected specifically to be critical of the protocol, to have academic insights with respect to the protocol, and to be a diverse and challenging crowd to convince. So the goal really was to make sure that participants were selected who would challenge it if something went wrong, who would not just say, well, it looks fine, there's no problem. Now, they had to upgrade their reference string eventually because they switched to a different snark. And in this updated system, they followed a similar multi-party computation approach, but they managed to scale things up massively by exploiting a similar kind of structure to what we exploit for the updatable reference strings down the line. And essentially, they allowed as many people as wanted to participate. It was a multiple phase protocol where participants could come in one phase, provide a part of an update for this phase, and provided that in each phase at least one update was done honestly, the system was secure. And it's then a reasonable question to ask, what does that actually leave to answer as a question? Because surely if anyone can come and update the protocol, update the reference string, and once they've updated the reference string, they can convince themselves that it is secure, then we're done, right? Because at that point, if you don't trust the security, you could have participated. But it still raises an issue, and the main issue is that you may not have participated in the update process. You may not have been able to participate in this update process and in the large multi-party computation protocol. Suppose now there's a new crypto boom. Suppose now you're looking at Zcash and you're trying to figure out, is this safe or not? Is this a secure system? You will still have to trust the users who participated in this multi-party computation. And that's fine. There's no issue with trusting other users. You can't just it's not possible to do this in a setting where you mistrust everyone. But there is a way in which it could be biased, and there's no way as someone externally coming into the system for you to verify that. Now, I have no issue with this, for example. I know personally people from both phases of the update protocol. In the first update protocol, I've met Andrew Miller. He seemed like a reasonable person. I would trust that he scrutinized this as much as he could, and I have no reason to doubt that is the case. For the second ceremony, one of my office mates and a good friend of mine participated himself, and I know for a fact that he did participate in good faith. He didn't subvert the protocol, and he will have deleted his part of the secret key. So what's the issue? Well, not everyone is as privileged as I am, and if someone's newly coming in and trying to convince themselves of the security of this, a reasonable doubt which they may have is, hang on, who organized this? Maybe they selected people who were going to collude. And there's nothing to prevent that, really. It's definitely possible for the Zcash developers who did select participants for both of those phases to select maliciously. And that's something which has to be considered. Now, as I said, I personally have what I believe to be good evidence that they did not do that. I do not think they would have selected my colleague if they had been malicious. But let's put ourselves in the mindset of someone who believes it. You can select parties who you know are going to collude and help you reconstruct the reference string trapdoor. Not only that, you can select people who look trustworthy, but who you also know are going to collude with you. And this is very hard to detect. In fact, it's probably impossible to detect. So there's an issue of trust in the entire selection process. And that's really the issue we're trying to solve with our paper, is to say, well, you don't need to have a centralized selection process, and it's fairly straightforward to decentralize that. Now, the main tool that we'll be using for this is the updatable reference string, the Updateable SRS. And there's a couple of Snark protocols which have updatable reference strings. The most notable ones, I believe, at the time are Sonic and Plonk. We did our analysis with respect to Sonic, but there's no reason to suspect that any part of it wouldn't apply to Plonk or any other snark with an updatable reference string. In fact, there's some subsequent work by some colleagues of mine that shows that it can also be applied to reference strings which are not updatable, which have slightly more complex structure to them. So if we have an updatable reference string, what that means fundamentally is that there are two algorithms. There's a probabilistic update algorithm, which if you give it a reference string as an input, it outputs a new reference string and a proof of this update. And this is really the key part of it, is the new reference string should be secure either if the old reference string was secure or if the update was done honestly. So essentially there's no way to remove the security of a reference string once added, and anytime an honest user updates, it becomes an honest reference string. In addition to that, there is a verify algorithm, which just takes a old reference string, an update proof, and a new reference string, and checks whether this is a sensible update. Now, to formalize this in the UC model, which our results are modeled in, we needed to slightly change things a little bit. Essentially, we needed to add more structure to the structured reference string to make sure that we can model the reference string without having to rely on the NISC prove and verify algorithms, as was done in the past. They were sort of bundled into the security properties of the NISC. And for that, we sort of try to figure out what is a reference string fundamentally, a structured reference string. And fundamentally, a structured reference string is just a trapdoor with a structure function applied. So the idea is you sample the trapdoor, you apply the structure function, and that gives you a reference string, where obviously the trapdoor is something you want to prevent falling into people's hands. So implied in that is that the structure function is a one-way function, so you can't just invert it to find the trapdoor. In addition to that, to model the updating, we allow permutations over trapdoors. And so essentially, instead of having a arbitrary update process, which gives you a new reference string, we tweak it a little bit to say, you take one of these permutations, and you can then apply this permutation to the trapdoor and prove that you've done that correctly. Now, you obviously can't apply it to the trapdoor directly, so we also need there to be a way to apply the permutation to the reference string directly. We call this a permutation lifting. And it all ties back in together with the old verification function, where basically the property we want is as a correctness property is that if you apply a permutation to the reference string and you prove that and you run the update proving algorithm with respect to this reference string and the permutation, then this should verify as correct update proof for the old reference string. Now, we bundle this into a functionality which, to contrast it with the traditional CRS functionality, just recall what this does. In the traditional CRS functionality, you just sample a reference string from a domain or a distribution, and then this reference string is made available to all parties, so it's essentially just sent to them. And you have this one point where randomness is sampled, which is then distributed to everyone. In our model, it's slightly different in that we first sample the trapdoor, send this trapdoor to the simulator or the ideal world adversary. Sorry, not send the reference string corresponding to this trapdoor is sent to the simulator. And then the simulator gets to select a permutation which it wants to apply to the underlying trapdoor. And once he selected this, the reference string of this permuted trapdoor is sent to all parties. So the simulator gets to apply an arbitrary permutation, but it doesn't know what the output will be, or rather it can compute what the output will be, but it can't figure out what the output's trapdoor is. It can just coerce the output by rejection sampling. So in addition to this model, which we formalize as a UC functionality, we need a couple of additional properties to actually be able to realize it. And the first of these is we need to have a way to simulate honest updates to the reference string. So in this reference string functionality, we essentially have a way to get the honest trapdoor, the honest reference string, because that's what's supplied to the simulator initially. What we still need to do is we need to then pretend that this came from an honest update proof. And the way to do that relies on a update proof simulation algorithm, where you take essentially a reference string which you know the trapdoor for, and you produce a valid update to a reference string which you do not know the trapdoor for. And I'll discuss a little bit about how that works in practice in a second. And the second and arguably more important part is that we need to extract the permutations from adversarial updates, specifically from their update proofs. And this is a bit tricky to do in the UC setting because it does not support white box extraction. So what we do instead is we use a second non-interactive zero-knowledge functionality, which in our case, or in the case of Sonic rather, is realizable by Fischlin transforming a basic sigma protocol. I believe it's a Schnorr proof of exponent protocol. And we can then extract from the random oracle used in the Fischlin transformation. Now, this is not particularly efficient. We essentially have a non-interactive zero-knowledge scheme used in another non-interactive zero-knowledge scheme. But first, this is a restriction of modeling. It's an issue with the UC model and not with the construction itself. And in a different setting, if we could use the algebraic group model, for instance, we could rely on that for extraction. And second, it turns out not to actually make a big difference in the overall scope of things. Update proofs are fairly expensive to generate and to verify, and generating and verifying a Fischlin transformed sigma protocol by comparison is almost negligible. And it still is one of the main reasons we want to have these structured reference strings in the first place is for efficiency. And the efficiency gains of having a faster non-interactive zero-knowledge scheme to use after we've done this is still preserved. So I want to give you a toy example of what a structured reference string looks like and what all of these algorithms look like in practice. In particular, what's usually the case is you have some group of a generator G and some prime order Q. And in this setting, often trapdoors are field elements in the prime multiplicative prime field of Q. And your permutations are then just multiplications with other field elements in the same prime field. Since this forms essentially a multiplicative group. So then the structure function is usually various exponents of the trapdoor. So you have g to the tau, g to the tau squared, and so on up to g to the tau n. And you may already see how to lift the permutations to apply to the structure of the reference string. So if you have multiplications of field elements in the permutations, then applying them to the structure which has exponents, you just exponentiate the individual parts of the structure function. So in particular, let's say we're multiplying with with field element A in our permutation, and this corresponds to exponentiating g to the tau by a, exponentiating g to the tau squared by a squared, and so on up to g to the tau n by a to the As well as that, we can generate update proofs by just applying an additional g to the a term. And you can then check with pairing operations that there is indeed this link between the g to the tau and the g to the a and the g to the tau to the g to the tau a. And you can also cross-check all of the values to make sure that the structure is preserved. And since our update proofs are just this g to the a, it's also fairly simple to simulate these update proofs just by inverting the trapdoor on the g to the tau term. So especially if you have your honest trapdoor, which you assume is g to the tau a, then you can just take this to the minus tau, and that gets you g to the a, which is your update proof. And yeah, for extraction, as I mentioned, using a official and transformed Schnorr proof of exponent, where you prove knowledge of A, makes A extractable for adversarial proofs. So now that we've covered the basics, I can finally get into our construction, and really we just rely on having a Nakamoto-style consensus, where the idea is every time we mine a block, we also carry out a reference string update. And eventually, so you update the reference string of the previous block. Eventually, because of honest majority, we know that the reference string will be secure. So specifically, if you recall that we have the chain properties of chain quality, chain growth, and common prefix, chain quality and chain growth combined tell us that there will be an honest block created at some point. And chain growth and common prefix combined will tell us that eventually everyone will see this. So if you combine all three, you result in knowing that eventually everyone will have seen an honest update to the chain, and everyone will know that. So if you do it for a long enough period of time, you can be assured that everyone will agree on the reference string, and that this reference string will have had an honest update. Now, there are then practical questions of how this, how long this actually takes, and I just realized that the epsilon values are cut off there. The dashed line is 10 to the minus 4, and the dotted is 10 to the minus 3. And so we ran this for several different values for what percentage of mining power was adversarial. So 45, 33, and 10% respectively. And there are two things that then still matter. As I mentioned, the probability of adversarial success epsilon that we're willing to tolerate, and how long the target difficulty is. And you see in this graph that there's a that these curves spike as the intended difficulty of blocks heads to 0. This is because there's a technique the adversary can use to essentially cheat and to create blocks faster than honest parties every time if the difficulty is too easy. Specifically, the adversary can essentially skip verifying, transmitting over the network, and actually generating update proofs itself. This is mainly because the most costly of these, the generation of update proofs, it can skip because it can simply select exponents which are very cheap to do. The main cost of exponentiating, the main cost of generating update proofs is exponentiating group elements. And if you pick a permutation which is, say, 1, or just the exponent 2, or something similar, then this becomes a very cheap process. And that means that no matter how lucky the honest parties get, the adversary will essentially always find blocks before them. Now, sorry, before I go on, I should, yeah, so before I go on, let me just go back. What this does show is that regardless of what you pick for these things, even for the 45% adversarial majority, If you run this on the order of a couple of months, you will get a secure reference string. Now, additionally, the same issue of cheating, quote unquote, in the update process is also an issue for rational miners. So while an adversary will always cheat because it knows that it can then more easily subvert the reference string, a rational miner will cheat because it knows that that will result in it producing blocks faster. And if this is all that rational miners are incentivized for, then they will cut out anything that results in them producing blocks more slowly, including the actual updates which they're intended to do. Now, this is an issue because if the rational miners use low entropy in their update proofs, then it's possible to extract from these update proofs just by trial and error. And as a result, low entropy update proofs directly threaten the security of the system, and we need to figure out how to address it. Now, it turns out it's not too difficult. You just get your permutations as outputs from a random oracle. And what this results in is it means that essentially you can only rejection sample the permutations themselves. And as a result, there will be sufficient entropy in each rational update to secure the entire system. Now, to actually enforce that rational miners select their permutations as outputs of random oracles, we do a cut and choose approach after the reference string has been generated. We select a subset of the users and ask them to reveal the pre-image of their permutation. And if they are able to do that, we give them a reward, which can then be adjusted sufficiently to actually incentivize miners to do it. So to summarize, we have a new model of updatable reference strings, which is now modeled in UC and gives more structure to what we have, to what has been there before. We apply Nakamoto consensus to securely realize this in the UC setting, and we analyzed what the practical implications for the parameterization of a ledger is and how to address the incentive misalignment that naturally arises in this situation. That is all I have for this presentation. I would very much like to see you in the live session and hear any questions you have. See you then.